Hello, here is a video about, again, magnetism and currents, but this time I'm going to talk about the magnetic force of a current carrying wire on a current carrying loop. Now, it's really just the force of two parallel current carrying wires done twice. So if you've watched the previous one about two parallel wires, you're in pretty good shape. You know the basics, and it should be just, oh, I do it once, I do it twice, add them together. Not too bad. Don't be too freaked out about all the things here. So we want to know the net force on the loop, on this loop, and I'm going to call it square even though I didn't draw it like that, because of this current carrying wire. So just conceptually to think about it, we want to know about the loop. So imagine I'm the loop, what do I feel? There's a current carrying wire, and that current carrying wire is going to create a magnetic field around it, which means that if I'm the loop, I am sitting in a magnetic field. And so I need to know what the magnetic field is that I'm sitting in, and then I need to say, okay, what is the force of that magnetic field on me, a current carrying loop? So that's what we're going to do. And I'm going to show you a way to try to keep track of which currents you want to use. So to start, again, I1 is going to create a magnetic field. So I'm just going to draw I1. I'm not going to draw the loop. I'm just going to say, okay, I've got I1, and I want to know what the magnetic field is from that current carrying wire. And I want to know what the field is at two different points. At these 2 points where the two parallel bits of the loop are. I don't need to worry about the left and the right pieces of the loop because those will not, those two forces, we can ignore them. They are zero. If we have the perpendicular, the force is zero. The other way to think about why we can ignore these two, okay, the magnetic field is bigger closer. So if I start here and go this way, the magnetic field I'm in is getting bigger, which means the force I feel is getting bigger. But if I go this way, then I'm starting with a big field and a big force and going down to something smaller. And because these have opposite directions for the current, one's going up, one's going down, you have equal and opposite forces, and each one of these little bits of force are going to cancel each other out. So we don't need to worry about the perpendicular pieces. We only care about the pieces that are parallel. So let's focus on the parallel pieces. So the one that's 20 centimeters away, so I need to figure out the one that's 20 centimeters away. And then I also need to figure out what the magnetic field is up here at, okay, how far away would that be? Well, if this is 20 and this is a square of 30 centimeters, the total distance here would be 50 centimeters. Now, what direction is the field? If this is my current carrying wire, and the current's going that way, here's right-hand rule number 1. Thumb in the direction of current, your fingers curl in the direction of the B field. So the B field is going like this. So right here above, it's going into the page. Below the wire, it's coming out of the page. So the magnetic field above this wire into the page. So that's my X's. So everything above the wire is in a magnetic field pointing inward into the page, I should say into the board, huh? All right. What is the size of that magnetic field? So the magnetic field at 20 centimeters away will be mu naught times the current, and now this is the current that's causing the magnetic field. That's I1. I don't have my loop in here. I2 is not part of this problem. Not yet. So current number 1 is 10 amps over 2 pi times the distance from the wire, and I'm going to start with 20 centimeters, but again, meters, 0.20. All right, so if I calculate that, I get 1.0 times 10 to the minus 5 Teslas, and that's into the page. And magnetic field at 50 centimeters, same thing. It's the same wire causing the field, so it's still the 10 amps, but now I am 50 centimeters away, 0.50. And this will be 4 times 10 to the minus 5. I don't like that number, but I'm going to just trust that it's good. I don't like that number. Okay. I think there's an error here. 10 to the minus 6. That makes me happier. Okay. 4 times 10 to the minus 6. Okay. So now I know from current carrying wire number 1 what the magnetic field is from that 2 places, here and here. And those 2 places correspond to the points where the loop is. Now I1 has done its job. We're done with I1. Now all I care about is my loop in my magnetic field. So I have a loop in a magnetic field. Let's draw that loop. Square loop, square. And we want to know what the net force is, the total force is. So I'm going to have the force from 4 sides. I can do the force of the top, the bottom, the left, force of the left, and the force on the right. But as I just said, these 2 do not have any force acting on them, so it's just going to be those 2. There's a force of a current carrying wire in a magnetic field, force of a current carrying wire in a magnetic field. What direction is the current? We're going this way and we're going that way. All right, so now what we do is we say, okay, let's calculate what the force is on top, what the force is on the bottom. So the force on the top bit of the loop, okay, and that's ILB sine theta. So the current, and now this is the current of the thing that's in the magnetic field. So that's the current that's going here, which is I2, which is 40 amps. The length, what is the length I'm dealing with? It's one side of that square, so it's 30 centimeters, 0.30. And then it's the B field that it's in. And which B field am I going to use? Well, it's the one at 50 centimeters because I'm doing the top part. So 50 centimeters is that one. 4 times 10 to the minus 6. All right, so what do we get with that? 4.8 times 10 to the minus 5 newtons. What is the direction? Okay, so we need to know what the direction is. Here is our second right-hand rule, and I do my little shortcut here. Current of the top is going to the right. The B field is into the page. So what direction is the force? Okay, flat hand, fingers in the direction of current. And I don't know which way I'm going to go. So my B field is going into the page. So current that direction, B field in that direction. Curl my fingers into the direction of the B field. Thumb is the direction of the force. Thumb's pointing up. All right. There we go. We know the force that this bit of the loop feels. Do the same for the bottom. All right. And again, I have, if I'm the loop, I have 40 amps going around me. The side, the length of the side is 0.30 meters. And now the magnetic field at this point is going to be, it's got to be bigger because I'm closer to the wire. So, yep, so now it's that one. 1 times 10 to the minus 5. All right, so that gives me 1.2 times 10 to the minus 4 newtons. What direction? The current of the bottom, in the bottom part of the loop is to the left. The B field stays the same, into the page. So what do we have for force? I mean, I know it's going to be down, but let's just verify. So current that direction, and B field that direction. So current, and then curl your fingers to B, and then the force is downward. Yep. All right, we're not done. Don't stop here, because we want to know the net force. That's the total force. We know that on the loop there's an upwards force of this size, and then there's a downward force of this size. We need to just add them together. One up, one down, subtract the bigger from the smaller. So here's my bigger one, 1.2 times 10 to the minus 4, subtract 4.8 times 10 to the minus 5, And you get, let's see, 12 minus 4, ugh, I don't want 12 minus 4.8. I'm just looking it up. 7.2 newtons. Oh, times 10 to the minus 5 newtons. And what direction would that be? Which is the bigger one. The bigger one is down. So the net force on the loop is 7.2 times 10 to the minus 5 newtons, pointing downward. And that's the whole answer. And so the process, again, is just the same as doing two parallel wires, just we do it twice, once for that up top parallel bit of wire and then once for the bottom one. We don't have to deal with perpendicular pieces. And once we have those forces, add them together and we get our net force. So I hope this one is starting to make sense. And again, do lots of problems in different orientations, and that will help you, especially with the right-hand rules. But again, if you have two parallel wires with the same current, so like the bottom here, the same currents, this gets pulled down, same currents attract, and opposite currents, opposites repel. This should be repelled. So the top is pushed away, the bottom is pulled towards. Overall, we have a pull towards. All right, good job.